should not be noisy, I would say. Yeah? So, and that's my great pleasure actually to introduce today's speaker, that Professor Wolfgang Kreisig, who is a pioneer of Petri nets. And so everybody who knows what is a Petri net knows his books, I'm sure. And here, where we speak about Petri nets, perspectives, extensions, and actually there were already several talks about how to combine different aspects of systems behavior with Petri nets, and maybe adding some other perspectives. And now, so just we have a really interesting talk, and so just how to model reliable big systems. That's of course always a challenge. And so I'll give a word to Wolfgang. So just and we are very pleased that we'll know about this really new proposal, I would say. Yes, a solution even.
Okay, so Irina, thanks a lot. This is a joint work together with Peter Fettke from Saarbrücken. He is more in business informatics, so that means since 1 year, I learn a lot about business informatics from him. And he learns from me a lot of other things. So we speak about big systems. Yeah, the host has made it visible to everybody. That's okay. So big systems, what does it mean? It means business information systems, cyber physical systems, information infrastructure, smart cities, Internet of everything. That is big systems. And what do they have in common? That I have now a problem. I see all the pictures of yours on my screen, but I don't like to see you. I prefer my slides. How can I do that?
Oh, Wolfgang, you don't see your slide?
I see them, but on top of them, I see you.
But that's okay. So we see your slide.
Okay. So I just continue, and I guess what is behind that.
I think we have different views.
Yeah. So what do the systems have in common? These are systems where you merge real-life items, physical items, and processes in the real world together with software, to integrate real-world things and software. And the question is how to cope with this kind of systems. And of course, what we need are really good models and a modeling language for this kind of systems. And let me start in a very systematic way by looking at modeling in different scientific areas. So what we have is, on the one hand, physics and engineering, and there we have dynamical description of dynamical things. And what they usually do is they model everything with continuous models, with real numbers over the time. And the central concept there is continuous functions over time. So behavior is always continuous functions over time. And why do they do it, continuous functions over time? Because of the calculus. So if you have continuous functions, you can make derivations and integration and all this. So they have a deep mathematical theory behind their modeling technique. On the other side, what is informatics? Informatics is the science of the, and I cannot read what I have written here because your pictures are in front of that, the science of the digital. I think is it written here? Science of the digital?
So we can see your slides, okay. So just if you see them for yourself, then it's okay. For us, it is okay.
Yeah. So informatics is the science of the discrete world and of the digital world. And dynamics, in order to model dynamics, we need discrete models. Now I have got what I wanted to. The science of we have discrete models, and the central concept is discrete steps. So what we need is a modeling language which is as fundamental for digital systems as the calculus that we all know is fundamental for physics and engineering. And I think so far we don't have a decent theoretical fundamental basis for the digital world. And the question is, how can this be achieved? So I would like to achieve this by considering the two phases of informatics. And this is a distinguish two aspects of informatics that are usually not distinguished so often. So the one phase is the technological basis. That is, we have hardware, digital infrastructure, digital surface for the user, compilers, databases, any kind of symbol crunching automata. We have a lot of formal reasoning in this world of informatics. There is implementations and specifications, and we want to prove correctness in this world, and that means the implementation meets the specification. And we have an epistemological fundament, that is the computable functions. So this is here the classical world of informatics. Theory starts with computable functions, and on top of this, we make all this technology. I would like to have another look at informatics, and that is the applications. So in the application world, we have real-world items and processes, as we have in smart cities, for instance. We have a lot of business processes. We have the notion of digital twins. We have also here, we have formal reasoning. So not only in this, in the left world, also in the right world, we have formal reasoning. We have operational models, and we have requirements formulated more or less formal. And here also we want to show in some way that the operational model meets the requirements. This can be formal, but it's not necessarily formal. So what is the epistemological fundament of all this? And the point is, we don't have one yet. That is urgently needed, and that is what we need. And that was what I talk about. What is an application-oriented modeling language for information that is based on the view of applications and not based on the view of technology and of computable functions? Okay. So this very general starting point as a model of discrete systems has three dimensions. One is static aspects. For instance, there are purchase orders, there are goods in stocks, there are messages, there are invoices. The whole world of business has static components, and the question is how we would describe them. And we describe them as usual in informatics. We have sigma structures. Well, that sounds a little bit strange for some people. That just means we have symbols, and symbols have certain properties. We have algebraic specifications, as we have seen them for 40 years now in informatics. So we have that what logic is. Logic, Petri first order logic is also based upon. That is the world of static aspects in this three dimensions. The second is we need some dynamics. For instance, we want to submit a purchase order. We want to describe how goods are delivered, or we want to mandate a parcel, or to pack a parcel, or to update a database. So these are dynamic aspects, and I think everybody in the audience can guess how we model this, called this Petri nets. And then we have a third aspect, and that is only really important for big systems, that is architectures. So a big system is composed of some, what we call modules. So the customers of a business may be modules. The retailer is a module, the warehouse is a model, freight forwarder, suppliers. You may have any kind of modules, and in a very abstract or concrete way. So this is the world of hierarchies and architectures and composition of modules. And how can we cope with this? Well, that is the composition calculus, and that is in a way the only new thing that I show you. So this above here, this is well known, Petri nets are well known, and this is new. Okay, so let's start with the first dimension, statics. I give you an example without going into the details. So what is a typical structure? We have a very concrete structure example here. So we have some customers of a business. For instance, we have two customers named Ute and Max. We have articles that you can order. You can order shoes or you can order hats or pens. You have concrete goods, so your concrete shoes, hat and pens. You have dates, you have freight forwarders, etc. You have a lot of constants, you have a lot of concrete functions. So that's the typical structure. This is another structure, but it looks quite similar. You have, of course, other customers here. So everybody who has an ID card is a potential customer. The articles are now cars, small or medium size or large, which you can borrow for a while. The concrete goods are concrete cars, etc. So this is another structure, and this is a similar structure to the first one. And how do we compare or speak about those structures? Well, that is what we usually call a signature. So what is a signature? Or an alphabet, an alphabet with ordered elements. So here we have symbols. Signatures are in the world of symbols. We have constant symbols, we have function symbols, we have variables, and we can write, for instance, terms like f, bracket, opening bracket, x, closing bracket, things like that. And all these terms are on the one aspect just symbols, and on the other hand, they can be interpreted in structures. And for instance, this signature can be interpreted in the structure. So this is a sigma structure because it has the structure of the signature. And the other structure that I've shown to you is also belongs to the same signature. Then we in addition have some relations which are as well in the structure and in the signature. And here we have a big signature, that is the signature which is interesting for the example I've shown to you. Now you can say, you know all this very well, and because this is the basis of predicate logic. This is what first order predicate logic does. We have algebraic specifications that are just using this kind of display between symbols and what they denote. We have object orientation, we have functional programming. So all what these theories do, but not so much functional programming and object orientation, but the rest here, they have a calculus of symbols, and they have a real world that is what the symbols denote. Okay, this is all I want to say about statics. Now I go to dynamics, and they have two parts. And the first part is I will speak about runs or behaviors or executions. So what is a run or behavior or execution? You will say, well, that is what everybody knows. In programs, in Petri nets, whatever kind of system models you have, you say a run, it starts in a state, and then it makes a step, it goes to the next state, etc. You have a sequence of states and steps, and that is a run. So there's nothing else to be said about a run than that is a sequence of states and steps. And I will show you that this is not everything to say about runs. This global view of states and steps is fine for small systems, but it's not adequate for really large systems, because I think you will agree that the world is not going forward in global steps. A company is not in a state, and then it makes a tiny step, and then the company is in the next state. So that is a much too simple view on really big systems. So big systems are much more distributed, and the insight you should get now is that not only systems are distributed, but also single runs or behaviors or executions are distributed. And I'll show you an example now. The first notion I would like to speak about is the notion of a local state. So what is a local state? I start with a notion that is so well known to you because you all learned a little bit about first order logic. You know what a predicate is. And I give you a very simple example, the predicate of being a prime number. The predicate is being a prime number, and we all know the number 5 is an example of this where the predicate applies to. And this is true since Aristotle, he already knew that 5 is an example of the predicate 5 applies to 5. And we know that 5 is no, somebody interrupted me. No? So we know that 5 is a prime number. No, sorry, I said it's a prime number. And in the future, 5 is a prime number. So being a prime number is a predicate that is always valid. And what is first order logic speaking about? It speaks about predicates that are always valid. And now I look at a slightly different predicate. Is a predicate that is in our business, and the predicate says we have ordering customers. So we have customers in our business, and some of them are ordering goods. And of course, we agree that this predicate is not always valid. So in Aristotle's time, there was no ordering customers, and Ute was certainly not an ordering customer in his time. Maybe she is now an ordering customer, but she will not always be an ordering customer. So there's a predicate called ordering customer, and Ute applies to this predicate, but only for some time. And here we have another such predicate. It's called purchase orders. So Ute together with 3 elements is the purchase order. So what are the 3 elements? Here it is written. These are article items. P1 is shoes, or 2 pairs of shoes. So Ute orders 2 pairs of shoes. Women always order pairs of shoes. P2 is a hat, and the other P2 is also a hat. So altogether, she orders 2 pairs of shoes and 2 hats. And we have a lot of other such predicates. For instance, sorry, you cannot read this, but you will see in a minute why you cannot read this. So there's an inquiry saying, is there an item P2 available or not? And also here, is there something available or not? So these are just local states, and I say again what a local state is. A local state is a predicate together with an element. With an element where this predicate may apply to or not, and where it sometimes applies to or not. And this is the fundamentally new idea. We say a predicate is something that can be updated. So the extension of a predicate, that is the set of things where the predicate applies to, can change. So in this sense, first order logic is the theory of constant predicates, and what I'm talking about is the theory of dynamic predicates. And how do we describe dynamic predicates? Well, those who know Petri can imagine, we describe it by boxes like this. So here we say, Ute submits a purchase order, and then she goes from ordering customer to this purchase order. And then maybe some other activity that says, we disassemble the purchase order. So this is one purchase order with 3 elements. And here we inquire the availability of the 3 single elements. And in this way we continue. So here you see a part of a complex behavior. We have seen already these parts here, but here we see this inquiry goes to the database. The database may say, well, I have 1 head. So there's an inquiry, is there a head available? And it said, yes, there is a head available. And then the database has 0 heads. And there's another question if the head is available or not. And then it is not available. In this case, the database sends an order to get more heads to a supplier. And independent of what is happening here, there's something else. Namely, here is a question, are there 2 shoes available? And yes, it is acknowledged there are 2 shoes available. So this is a behavior where some parts are independent from each other. Okay, and here we go to a representation of the whole behavior. So I hope you remember what we have seen so far is just this little piece here. So then you see if a head is not available, then it is a message to a supplier, and the supplier returns a lot of heads to the warehouse, and the warehouse informs the inventory management, and then everything goes to the order management, and the order management orders in the warehouse that they should pack some parcels, and they should give the parcel to the freight forwarders, and they give that to the customers. Okay, so what you see here is one specific behavior that only occurs once in the whole life. There cannot be a second repetition of this because this is a unique behavior. Technically, it is a Petri net where every place has exactly one arrow going in and one arrow going out, and the arrow sequences are never doing a cycle. So the sequences go from left to right, but there is one place that has no ingoing arc, and this one has no outgoing arc, but the others are structured in a very regular way. And Petri himself suggested in the 1970s to use this kind of structure to describe behavior of concrete systems. So this is not very impressive when you have small systems, but in large systems like this here, it is impressive because this graph we represented now in a different way, which is this one. So here we have exactly the same graph. So please believe me, there are no cycles anymore. It is the same graph, but now we have structured it a little bit different. For instance, I go back now. The customer has a little part here and a big part here. So we put this together to the customer's part, etc. When the warehouse has some aspects here, some aspects here. So now we say this is the behavior of the customer. This is the complete behavior of the order management. This is the warehouse, etc. So we order this run in a different way. And now let's look a little bit into the details of the behavior of the customer. Now I can say what in this specific case, how the customer behaves. And he behaves like this. So the upper part we have seen already. Ute is ordering, she submits a purchase order, then she retains a copy. She will eventually get a message telling her at Christmas she will have got all the things she has expected. She expects a delivery, which was 1 P1 and 2 P2s, and what she really gets is 2 parcels, and that's surprising because she sent one order, she gets 2 parcels. In one parcel are two pairs of shoes and a hat, and the other parcel there is 1 hat. So that's not structurally, it is not exactly what she wanted, but she opens the parcels. So this parcel opening gives her 2 shoes and a hat. This one gives her another hat. So altogether, these are 2 shoes and 2 hats, and that's what she wanted. So at the end, she is happy with what she got. Okay, so you see this kind. You can go into the details of all the other modules, and then you see what happened in this concrete case. Okay. So now I have spoken about one specific behavior. Of course, that is not what we want. We want in the second dimension, so to speak, the system model. So now let's go from steps that we know already to step schemata. And that is also very simple. So here we have a picture that you know already. We have the predicate ordering customer, that was Ute. And here we have the predicate send order, that is Ute together with her orderings, and that was Ute submits this order. We have seen that already. Now I rewrite this a little bit, and I say, instead of saying the predicate applies to Ute, I say this is the predicate. So this circle is the predicate ordering customers. And what I see now, it applies to Ute. So it's exactly what I have told you here, but I write it down in a different way. And here the same. So send order, send submitted, that it should be the same word. Send order is a predicate, and in the initial state, and now I speak about state, initially it does not apply to anything. And now I tell you how submit order will do something. And of course, those who know Petri, for them it's almost trivial. So Ute is moving away from the ordering customers place, and what is written in here is it goes to the submit order, and the step is now going to this state. Ordering customers has no element anymore, and submitted orders has what we expect. Okay, the same story written down in a different way. And again, we go from this representation to a different representation, and that is this one. Sorry, we have again ordering customers with Ute and submitted orders with nothing initially, but instead of writing Ute on the arrow, as I write a variable in the arrow. So K is a variable, and here I write K and X. X is also a variable. And here inside, I say how I evaluate or how I interpret the variables. So K is interpreted as Ute, and X is interpreted as P1, P2, P2. And of course, this is exactly what we wanted. So we can make a step and we go to the state that we have seen. So why do we do this? It seems a little bit more difficult, but it should be of some use. And say you see it here. Now we can say, aha, there's not only Ute to whom the ordering customer predicate applies, but also Max and Ulf and maybe many other people. And aha, for this step I have here is now gained by this valuation of the variables. So that is what we know. But here we could also write some other variables. For instance, we could say K is Max and X is 2P1 orderings. And then we have another step here. And even more, we can write nothing inside. And then we have a lot of steps represented, saying you may freely choose anybody for the variable K and any kind of ordering for the variable X. And here we have a schema for how to submit orders. And this is a schema for infinitely many potential orders. So that's why I made all this journey. Now we have a system model. Now we are on the level of systems where we can describe very many, in fact, infinitely many single behaviors. Okay, so let's go back to the customer. Here we have the single runs. So it's just a picture you have seen already. And now I show you the corresponding system model. So here we have the ordering customers, Ute, Max, and Ulf. Here is the variable K. Here we have nothing. Here we have a variable K. This part you have seen already. Here we have copying orders. Here we have received messages with the variable K, X, and T. T is a variable for data. Okay, and here you see deliveries and the accepting of goods. Here we have a very big problem because, as we have seen in the concrete run, that the things we have ordered, P1, P2, P2, does not very precisely correspond to what is delivered. Here we had an example with 2 parcels delivered. Here we can get 3 parcels or just 1 parcel. So what we have to show that this is really correct is we have to open the parcels, and that means we have an operator that is called element, and intuitively you may just say I explained the element up here. I think here you understand it easily. Here we had Ute as 1 ordering customer. In the other example, I had 3 ordering customers. That was Ute, Ulf, and Max. But what we want to show in the system level is to say, here we can have any set of ordering customers. Not only 1, not only 3, but whoever is a potential customer can be an element of ordering customers. So what we may try to do is we have a variable of the type set of customers. And then you interpret it to say with everybody who has a passport is a potential customer. But so we could write just a simple B into this place. However, when we do this, when we only write B here, then K must be validated by B. But that is not what we want. We want K to be validated by elements of B. And this is a fundamental operator, this element operator. So that means what is written here is that not B is an element that ordering customers applies to, but all the elements of B are elements that apply to this predicate. And the same is applied also here. So now we have a very liberal way to speak about systems. Okay, so here we have now a system model which resembles to you the system model of the single run, but now it is a system model of the complete system. We have the customers here, the order management system here, inventory management system, the warehouse system, supplier system, etc. This is a formal model. This is a Petri model on a schematic level. So the inscriptions are only symbols and terms. And on this model, on this level, you can formally prove, for instance, things you want to be true. Each order is eventually served. So when somebody orders here something, then eventually he gets the ordered things. And vice versa, a good that is delivered here is only delivered if it has been ordered before. Okay, so Petri people know how to prove this by, it is proven by place invariance and some arguments about absence of deadlocks. Okay, for instance, each requested reservation is eventually acknowledged. That is, here is some reservation of goods, and eventually the reservation is acknowledged. Either it's acknowledged directly or it is acknowledged after the supplier has supplied the missing object, then it's supplied this way. Or each mandated article has goods in a shelf. That means if the order management tells the shelf, please pack this and that parcel, then it must be clear that the corresponding goods are in the shelves. And all this kind of stuff we can prove on this level. Okay. Now I come to the third dimension, and that is architecture. But you have seen already here that this big system apparently consists of 4 components, which we call modules. So these are, 6 modules. These are 6 modules. And the question is how to represent the composition of modules. So far we have seen nice pictures, but we cannot be sure that there is a formal background of this. And I show you now, and this is the really new thing that also passionate people may not have seen already. I show you how to define composition of modules. And here we can do the following. We have the modules, as I said, customers, order management, inventory management, etc. We just write them in a row, and there is a composition operator, that is this dot, and we write it like that you see here in a sequence, and we compose this sequence, and that is what we get here. Formal definition comes in a minute. Here we have the representation, I hope you remember this, of the single run, which I started with. So customers underlined is the single run as part of the customer. And order management underlined is this. And how can we compose the components of the single run? But in exactly the same way, with exactly the same composition operator, only now saying customers underlined is the behavior, this one behavior of the customer, etc. So again, the composition of the run components is exactly the same composition as the composition of the system model. So here we had this very many parts with the snippets. The customer was, the single run was here a little bit of the single run of the customer, and here a little bit also the warehouse, here had a little bit of behavior, and here. And how, here again, we can ask how we can represent the composition of those snippets. And you can guess already, if we denote the snippets by A, B, C, D, etc., we just write the composition like this, and that's it. So this is apparently a very flexible operator. You can compose everything with this kind of an operator. And the question is, of course, how is it defined? And I'll show you the definition by an example. So here, this is a module you know very well. This is the customer's model of the system, on the system level. And now we make an observation that you have intuitively seen all the time. A module like this one has an interior part that is everything within the yellow box, and it has a surface that is everything on the yellow box. And the surface consists, and this is a little bit surprising maybe for you, it consists of two interfaces. And one is denoted as star A, and the other one is A star. So what is star A? That is everything that is on the left side. So we have here two elements, ordering customers and accepted overall delivery. These are the elements of star A, and A star has these three elements, okay? Now we have the module of order management. It also has a left part and a right part. And on the right part, it is not so important for the moment. We have these three elements. On the left part, we have those two ones. And now we see the elements are labeled. For instance, here is written purchase order, and here is also written purchase order. So the idea is, as they are labeled the same way, we compose them. So we compose everything as far as possible. So we compose those two, and also messages have the same label. So we compose those two. Now you may ask, how is this composition defined? So graphically, it looks like in a Petri net, and the black square here looks like a transition. Well, if you want to make it like this, you could do this and have another component inside here. But you also can do it differently. You just glue together the purchase order places. And I think this is for the moment the better way to think about this. So you glue those two places, and also you glue those two places, and then you have composed A and B. The problem is, of course, what about this place? This poor place has no partner in star B. So what will we do with this? Well, it goes to the right part of the composed system. So it goes in a way to this place here. So the composed system AB on the right side has those three places, and in addition, this place. So this has 4 places on the right side. What about the left side of the composed system? It has those two elements which have been the left side of A star. So in case star B would have some other elements that have no partner in A star, they also would go to the left part of the composed system. Okay, if you got it, that is the whole definition of the composition operator. And now we can start to use this composition operator also to make refinements and abstractions. For instance, I can say the whole business that you have seen so far is one module. It's called the business module, and it is just a big box, and its left surface has 2 elements, ordering customers and accepted delivery, and the right component, the right interface has nothing. And now I can say, how is this business module, how is it composed? Well, I compose it this way. I have the customers part here that we know very well. We have the supplier part here, of which I have not said too much. But here we have the elements of the joint labels. We have the freight forwarder, and we have the big retailer, which we remember was itself consisting of some components. But at the moment, we have just one retailer, and the business is now defined as customers composed with the retailer, composed with the supplier, composed with the freight forwarders. Okay? And now we can ask, well, how is the retailer defined? Then we refine the retailer, and we can say, well, the retailer here, this retailer itself can be written as a sequence of those 3 components. And that's also, you see how flexible is the composition operator also when it comes to refinement and abstraction. And now if you ask how is order management defined, then you go to the definition that you have seen. And you see here already that you can have composition of components, of modules on different levels. For instance, the customer is already on the behavioral level, whereas, say, freight forwarder is not yet under the behavior of the behavior level that you can still refine and give it and go to the level of behavior. And also here, retailer is refined to 3 elements, etc. So the composition operator is very nicely compatible to the refinement and abstraction. Okay, here you have your refined view that you know already. And of course, you say the business is just the composition of those 6 elements. Okay? So I'm almost finished and I conclude, but our conclusion is not very quick. It takes a while. So this is, say, the abstract framework of this thing, what we call HERAKLIT, which is a whole world of component of concepts, and we will have a lot of software that supports all this. But in the moment, it is just conceptually supporting the modular to express their ideas. It allows the modular to freely choose the level of abstraction. And this is very important. You can, in one part of your model, go to the details. In another part of your model, you go to an abstract view, and then you refine the abstract view, you abstract the refined view, and that goes very systematically. It allows the modular to freely choose the kind of composition. Well, this should come as a surprise to you, because on the one hand side, I say composition is very simple. It is just melting equally labeled elements. And this is not a very way to freely choose kind of composition. Because if you look at literature, there you find very sophisticated composition operators who do have a lot of additional requirements when composition is possible or not, and what composition makes with the data that are moving from one component to the other. So how can I dare saying you can freely choose all this, when on the other hand I say composition is just gluing equally labeled elements? But the trick is that when you have a complicated composition operator, which I just described by star is, you have any kind of composition complexity here, then I say, do all these complex things into an adapter. And so make a third component, which is called adapter, and place the adapter between the components A and B that you want to compose, and then then compose A in the very simple way with the adapter, and then you compose the adapter in a very simple way with B. And all the difficult things and sophisticated arguments that you have in your composition operator, you place it into the component of an adapter. And that turns out extremely useful as a, say, best practice argument. Okay, what we generally said, we avoid concepts that may suit small components, but do not suit large components. And most important, we do without the notion of global states and global steps that update global states. So there is no global view in this world. And that is important, for instance, when we have, you may remember the case of, go back here we had a supplier, so that may be a supplier who just I just model here, whenever you ask the supplier to supply some more goods, he does it. But of course, it may be that the supplier himself does not have available all the goods you want, so he has to order this at a factory. So you say, hey, I have this system model, and I also want to tell the story how the supplier ordered things at a factory. So no problem. You build another component that only interacts with the supplier, and the rest of the model is not affected. So no global whatsoever is a fundamental aspect of HERAKLIT, and only with this they are saying we have a modeling technique for really big systems. Okay, that's what I said here. But there is a small thing of globality. There is you may have some globally valid names, and if you really have them, then you can deal with them and rename them, or you may also keep them. Sometimes you have reasons to keep them. Okay. Everything is highly compositional, and that means that whenever you have some knowledge about components, about modules, then you can derive some properties of the composed system. So HERAKLIT integrates established concepts with a new one, that is task structures and signatures as in logic. So in a way I say, just take first order logic, we steal all the concepts of first order logic and just apply them in HERAKLIT. That is why the formal framework is so simple, because we just borrow everything from logic. We have Petri for the dynamic part, and distinguish, however, very fundamentally between, and that is not done so frequently in Petri, between the purely symbolic level with the signatures as is done in logic, and the interpretation of the signature as concrete systems, that is then a system level of Petri. And then as a third level, we have single behavior, single runs. So Petri in this sense is not just system model and behavior, but schematic level, and then system model, and then behavior. And I give you an example where we use this. We have a schema describing how a bank runs its branches. So assume you have a bank, you have a lot of branches of the bank in the town, and on the schematic level you describe how the bank organizes the branches. Now you want to describe the single branches. So on the schematic level, you have the principles, and on the interpretation level, you have every single branch, because every single branch, it looks a little bit different. One has 3 people engaged, one only 2, etc. And then on the third level, of course, you have the single runs. Okay. And then you have the composition calculus that allows you to describe really big systems. Okay. HERAKLIT only works on the basis of some fundamental theorems. And in some way you disappointed me a little bit, because all the time I had expected you to interrupt me and to say, well, this cannot be so simple, because I go back to give you my point. You see it, for instance, here. I just compose these 6 elements, and I compose them without any brackets. So of course, it may be that if you compose customers and order management first, which is again a module, and then you compose inventory management, it may in principle be different from first composing order management and inventory management together, and then from the left, add components. So how can I write all this without brackets? Well, I can write it without brackets because the order does not matter, because what we say in mathematics, this composition is associative. And now I go here. Because this rule holds, if you compose B with C, and then from the left to A, the overall composed system is exactly as if you would first compose A and B, and then from the right to C. This is absolutely fundamental, and this is not at all trivial, because if you start composition a little bit different, like everybody would start with, that is, you have components, you have an interface has elements, element has labeled, some elements are labeled on the interface. Now, if you compose 2 components just by gluing equally labeled elements, and then you have the composed system, then by surprise, this is not associative anymore. If you do it the simple way, it's not associative. And that is some publications simply ignore this. They define what composition of two is, but don't even, they are thinking about three, and then they pretend it is associative, which is in general not. But that is usually done like this up, and many of the formalisms are by chance associative, but not by proving that. So for this kind of composition operator, I've proven this, and this is fundamentally important. And compositionality means if you ask what are the properties of the runs of a composed systems, well, then sometimes we can say, take the runs of the first system, the runs of the second system, and compose the runs. This is a little bit cheating. It's a little bit too simple a representation, but in principle, it works like this. And as I said already, composition is extremely expressive because whatever you can want to smuggle into the definition of the composition, establish it by help of an adapter. And of course, here you see how important associativity is, because it's completely irrelevant if you compose the adapter first with the A and then from the B from the right, or if you put the adapter first with the B and then A from the left. So without these basic fundamental theorems, I would not have shown you what I have shown to you. But as this is true, you can model, you can combine and verify many aspects of your system, and then you can do it with any, I just say it like this, with HERAKLIT, you can do things that you cannot do with any other kind of system model. Not with any of these 1,000 variants of complicated Petri nets, nor with BPMN or other modeling techniques of the business world. Here we have a combination of technically very simple things, very well established things, and very many proof techniques. So this brings me to an end. HERAKLIT is the infrastructure to shape statics, dynamics, and architecture of computer-integrated systems. If you want to see more, if there's somebody left from the audience, which I cannot see, then you can look at this website where you can see many case studies. So I should tell a word on this. We did not start with a theory. We started with many real-life systems, examples and case studies, and those you can find there. Okay, that was my point. And now I want to go back and see the participants. And first, I thank you for your patience.
Thank you very much, Wolfgang. So it was very interesting. And now there are some questions.
Well, you must tell me how I don't see anything, anybody, but I would like to see the audience. And I don't know how to do this.
So you do not see? So you maybe, so look at the view in the, so just right up corner and then choose a view with the gallery.
And also maybe Wolfgang, but if you do that, you will not be able to show your slides anymore. You could unshare your screen, and then it automatically should go into the gallery view. But then you will not be able to show your slides anymore, which may be useful during question answering.
In the meanwhile, I can see all the single names, but I would like to see all the audience. And I only can see the single audience people. Okay, so I look to the simple. Who was talking? Marco, it was you?
Yes.
So I try to see you. But I cannot see you. I cannot see anybody.
So I think it is possible to see both slides and the gallery, but you maybe should change this view.
Are you seeing, Wolfgang, at least something about the participants somewhere in your screen or not?
I see that there are 18 participants.
Okay, and in that part there is no set of icons like with a grid or something like that.
I can invite them.
No. We are all here already.
Yeah.
So then maybe to switch off the demonstration for some time, and then
I can stop. Should I dare saying stop?
yes.
Yes.
Stop. Yes.
Aha! Great. Now I can see everybody.
Yeah.
Good.
Wonderful. So Marco.
So thank you very much, Wolfgang. Now I understood more about the philosophy of the approach. Maybe ask some questions for which we already had some exchanges, but you know, I would like to hear more about that. So I have basically three questions that are of interest for me. At this level, there are many more, but they would go into too much into the details. So I think we could exchange then offline some interactions on that. So the first question is about the modeling of the data part, right? For which you very cleanly rely on first order logic. Now, my question would be, why didn't you use more of the language that you could get from first order logic to manipulate what you have in these tokens? And in particular, there was something that more specifically attracted my attention while you were presenting. I've seen, for example, that in some of the slides you were showing, you used both multiplicity of tokens to represent the occurrence of multiple items of the same type, but you also added the number of items inside, which sounded to me like a sort of representing the same aspect in two different ways, right? In the sense that I could have two tokens labeled by shoes to say that I have two pairs of shoes, or I could use this term structure that you were using where you had the shoes, comma two, right? So I wanted to know a little bit more about this representation language and like the querying aspect of that in the dynamics.
Yeah, this I learned from business people. These are two different things. So if I order in one order 2 pairs of shoes, that is one thing that I order. And then they may deliver to me 2 parcels, each parcel with 1 pair of shoes. So then I have 2 parcels. So 2 single pairs of shoes is completely different from one ordering of 2 pairs of shoes. So I need both. I need, say, in the order I want 2 of that, and on some other level I want the 2 things as 2 different things. That's what they provoked me, say, can you model this? Can you model that? And I say, yes, I can. With this simple, say, multi-set stuff that we always have in Petri nets anyway. And that's why I did it, because they provokingly asked me to be able to do that. That's it. Does it answer your question?
Yes. Yes. So this
is what I said to you.
It hints about the identity of what you have. So would be curious to see how much you can leverage on that to model things differently, and to see whether then this would have also a difference in the formal aspect of that. But I understand the representation aspect of it. Yes, sure, from the conceptual point of view.
Yeah. At the end, of course, you want to prove that when you order in one order 2 pairs of shoes and you get 2 different pairs of shoes, that this is what you wanted. So you want also to have an equality of both. But that can be done very simple in this multi-set framework of Petri nets. And I agree with you on, as a theoretician, you would say, But that's redundant, that's not necessary. Why do you have both of this? But now I'm a business people, and now I say, because I want it. And when I want it as a business people, the theoretician has to do it. Okay. Yeah.
So I have a couple of other questions, Irina, but I don't know if you want to let others intervene. So just.
So Anna has written a question. Maybe you just just say it in voice. Anna. So Anna doesn't hear them.
Hello.
Yeah.
Hello. Thank you very much for interesting presentation. But I have some questions concerning the analysis of the model that you presented. What kind of information about the process can we get from the model, and how we can automatically analyze it, and how I can understand what wrong with the process, what can be better, or maybe how I can verify it automatically?
Well, these are very general questions. Of course, when you want to verify something, you have first to describe what you want to verify. So you have to describe the property that you want to verify. So we have to speak about properties. And of course, here again, that is, as we're so close to logic, then we can use a lot of logic also to describe properties. Of course, what we also need is a little bit of temporal logic, or aspects of temporal logic. The problem is, however, that temporal logic operates on global states and steps. And that is what we want to avoid. So we need a kind of a temporal logic for single components. And that was what we are working on, and is not yet finished. The other of your questions, I can't really say too much about. Can you repeat it?
Thank you very much.
Okay.
Yes, then maybe Mark.
So maybe on top of what you said, Wolfgang, because I also had a question on which type of logics you want to envision to verify properties, right? And yeah, so I expected like an answer from you precisely on the fact that you don't want to have this global operator, right? And maybe you also don't want to have so you want to have logics that talk about partial orders, right? Because here you have traces that are truly concurrent, concurrently combining like the evolution of components, right? But maybe can you also comment about where do you believe you will get some sort of decidability conditions for checking these properties? Because, you know, if you just approach the problem so generally, then you end up immediately into high undecidability. And you cannot really even restrict the logic, because even restricting the logic would not suffice, right?
Yeah, you're completely right. The first thing is, of course, what we would like to have is a, say, temporal logic on distributed runs. And in a way, there exists one. Maybe you, but I tell it as follows. Some 20 years ago, I've written a thick book about distributed algorithms. This was no success. This was a book that has rarely been quoted because it may technically be a little bit difficult. However, there I have described precisely how you can deduce on the symbolic level some, say, liveness properties. That is what you exactly need on the symbolic level of temporal logic. This technique is far from decidability problems, which of course on the other side means you are far, hello, how are you? Which of course means on the other side, this is far from being complete, because if you have no problem with decidability, you cannot express everything that is valid. But yeah, this is still to be done, and this is only can only successfully be done if you now start specializing the kind of components you compose and the kind of composition you have. Maybe I should say a word on the composition. In this example, you have only seen that places are glued together. Equally labeled places have been glued. The formalism is absolutely neutral. If you have two transitions and you want to glue them, so glue them. And we even made case studies where we cut some arrows in Petri nets, and then we glue parts of an arrow. So this is liberal. Of course, in this general framework, you may see you have no chance for a general verification technique that allows you to verify everything that is true without running quickly into these decidability problems. All this is still work to do, and invite everybody who is listening to me to join us in this effort. There's so much to do, to be done, and it is so important because it's so fundamental. So it would be a good contribution to science if you look at this, and there's so much to be done. Okay.
Yes, Vladimir, please.
Thank you. Thank you, Wolfgang, for your nice talk. It was well interesting. I have a question about the non-determinism. Your models, your Petri nets, are models for runs, so they do not have choice.
A single run does not have choice, that is true. But a system, of course, has choice.
Yes, but I think that non-determinism is well useful for modeling.
Absolutely, yes.
How it is introduced in this model?
Well, you see, I started with a single run. And a single run is something where you have decided all the choices. But then on the systems level, where you have, well, already in the starting state, when you start with ordering something, you have infinite non-determinism, because on the system level, you can order whatever you want to order and whoever wants to order something. And then later on, the shop has a list of things you want to have. The shop will decide which parcels will be compiled. Will you get everything in one parcel? Will you get something? Will they make 3 parcels? And they have completely free choice in separating what you order in parcels. So there's a lot of non-determinism in this example. And any kind of non-determinism that you can model in Petri nets, you can model also here.
Yes, thank you.
Yes, Jan Martijn, you have a question, yeah, please.
Thanks a lot, Wolfgang, for the very great talk. It reminds me lots of the discussions we had way back ago when I did my PhD on composition and how to discuss properties if they are spread over multiple components. So yes, I'm very interested to join and to have a little bit more of those talks into what happens. But I was just intrigued by your run operator. And so the composition of the run. You said run A, B is run A composed with run B. And I was just wondering, what are the tricks that you're doing there?
That was a little bit cheating. It should, at least you should say run of A composed with B. You have the set of runs of A and the set of runs of B, and then you compose every run of A with every run of B. Okay, so you are completely right. At some places, I must admit, I have cheated you. And this was one of them, but not the only one.
Yeah, so
okay.
It's fun to have
just for the sake of beauty and simplicity. Okay, yeah. And you got me. Okay.
But I really like the approach of having those compositions and start thinking in terms of larger components. I think that's some of the things that we really miss in Petri nets and thinking in larger systems. So thanks a lot.
Thank you, you're welcome. And look at the web page.
Yes, and Marco, you have more questions, yeah?
So maybe a last question, Wolfgang, on my side, related precisely to what Jan Martin was asking now, whether you can tell a little bit more about the way you compose things, in the sense that there may be, on the one hand, sometimes ambiguity, right? In the sense that you may have multiple labels matching, so there will be non-determinism in how you match them. And the second question is, there was the example that you showed where you were matching on the one end at the schema level, but on the other hand, you were showing how to match at the run level. And there at some point that you concatenated, I think, 3 letters, but by looking into the picture, it seemed to me that 2 of these were in parallel. They were not sequentially composed.
Okay. So, now these are 2 questions. So I started with the first question. Assume you have a component A, and on the right interface of A, you have 3 elements labeled A, B, and C. And so the idea is you want to say, I am only interested in components where in one interface the labels are all different. Because if they are all different, then you can compose nicely. Well, the world is not following all your wishes, because when you, from the left-hand side, there can come another element from, if you compose Z, A, and B, then from the left there comes an element from some other component which has also the label A. So you cannot avoid, by composition, to have elements with the same label in one interface. So the problem is, what will you do in this case? So you have component A, which has on the right side 2 elements. Well, assume all elements have the same label. In the extreme case, you have only one label and all the interface elements have the same label. That can be the case too. And then you compose A with B, and if the right component of A has 2 elements with the label A, and the left element of B has also 2 elements with the label A, then you have 4 ways to compose them. And then, yeah, that also took me a while to do something. Either you say, it's non-deterministic, you have 4 ways to compose them. That is not good at all. If you want non-determinism, then make an adapter who does the non-determinism. So the right solution is you want to have it deterministically, and that means you have on equally labeled elements, you have an order. In addition to the labeling, you have an order. And then you compose the elements with the same say, size on the order.
Mm-hmm. So you say, give me the first A and match it against this other A that I have in the component I want to match. So you can really pinpoint to the exact element that you want to match. Perfect.
Exactly.
Okay.
The first, the second. Yeah, that's what you need. And with this, it's yeah. Of course, then it's not, you must prove that it's associative. So you can imagine that this proof of associativity is not too simple, because you have a lot of requirements to this. And by the way, I don't know any other composition operator in the world that is associative, deterministic, and in a sense total. That means take any 2 components with any labeling of the interfaces, you can compose them. And that brings me to your other question. So assume you have 2 components and their labels are completely different. So one has labels A, B, C, D, E, and the other one has, say, Russian symbols, okay? So they don't fit, or maybe Russian symbols that don't happen to look like Latin symbols. Okay, so what happens then if you compose them? but that is purely parallel composition in this sense. Then you have a component that consists of two separated elements, and the left of this component has some some Russian and some Latin elements, and on the other side you have also some Russian, some Latin. Okay, and this happens to be even you can, in this case, A composed with B is equal to B composed with A, which is, by the way, a property that is sometimes nice to have, but not at all important. So when modeling big systems, you never say, how beautiful would it be if AB would be the same as BA? You never need this. What you need is associativity.
Thank you very much. Thank you very much, Volkan.
Yeah,
Very clear.
Well, another question about the composition operation. Is this always acyclic? So there are no cycles introduced by modules?
In a single run, yeah, in a single run, there are no cycles, yeah.
But if you compose different modules, then...
Yeah, on the system level, and what I've shown to you, of course, there have been cycles. On the level of the system, there are many cycles, yes. These are any kind of Petri structure with any kind of, only a single run. And I remember how much people have a problem conceptually to understand what a single run is, because it's the way how we teach informatics. We teach students from the very beginning that a single behavior is a sequence of states and steps. It's in programming languages, it's in automata theory. Wherever you look at people, you think, of course, a behavior is a sequence of states and steps. Or the language theory goes like that. And to go away from this and say, no, a behavior is, of course, acyclic because everything happens only once, but it may have concurrency inside. And still it is a single run. That is difficult to understand for people who are, say, badly educated in informatics. By the way, for business people, this is simple. They understand this immediately, much simpler than computer scientists.
Okay, so thank you.
Yes, so more questions? So then maybe I ask a question. So just, I wonder if I understand it in the correct way, but the main idea is to compose not models, but runs, concurrent runs, and by that to somehow simplify the understanding and verification. And if there is a chance to do verification compositionally, on this level, because when we compose models, we know that compositional verification is almost always so just not possible, actually.
Well, be careful. I talked a lot about single runs and about their composition, but the HERAKLIT approach is about systems. It's mainly about systems and about schemata. And what I said and what you said and asked about verification is not yet written down in detail. There's much work to be done. And again, I invite everybody to do this. We are not so many to do it all by ourselves.
I see. I mean that when you have this so just runs without cycles, deterministic, then it should is somehow verification. So
good point, yeah. That is an interesting point, because many verification techniques do not exploit this fact that there is no choice. So what I've also seen is that systems in business informatics are sometimes very simple. At the end, the single system is not complicated. No cycles, not so much, very simple. Do A and B, and then wait for a message from outside and do either C or this. So this kind of systems they have. And our verification techniques do not exploit that things can be so simple.
Yep.
So in this sense, it would be useful to have verification techniques for very simple models.
So I think that's really a very good direction to work in, because yeah, of course, so just people try to do two general things. So suit for everything, and to find application areas where we can do it in a simple way. So that's great.
Yeah.
So
I have one more question, or ask for clarification. In the field in computer science, there is a large field in concurrency modeling called process algebras. Are there any relations between these fields?
I didn't understand one word. What kind of algebras?
Process algebras.
How do you call broadcast algebra?
Process.
Process algebra.
Yeah,
Process
exactly.
algebra. Okay. No, process algebras are so different from what I told you here. The composition operator of process algebras it's another word. So they have one equation that ruins everything, and they say A parallel B equals
Mhm.
either A followed by B or B followed by A. That's how they start with, and that means they have no clue what concurrency is, because this equation ruins concurrency.
Okay.
It goes exponential in the size of a system, because they consider all the interleavings. They just have no idea what a partially ordered run is. So that's a different world. I am amazed how successful they are, or they pretend to be, but for really big systems, they don't have anything.
Okay, thank you. And actually, I have one more question
Yes.
regarding. You told that there are 3 dimensions of a system, and one of these 3 dimensions is architectural or architectural dimension. And what is in many modeling languages, for example, in very practical UML models, they usually say about 2 dimensions, like structure and behavior. What is the importance of this 3rd dimension, of this architectural dimension in your language?
Well, you can say structure and behavior relates to architecture and dynamics, and then what they are missing in this structure and behavior world is the statical aspects, so the data aspects. In UML, you frequently don't talk too much about data. So in my terminology, they speak about architecture and behavior and dynamics.
Okay, thank you.
So any more questions? So actually there were many questions, and thank you once more for very interesting talk. And so we have enough what to think about now.
Okay, yeah. I thank you, and look at the website, look at the case studies, and there will come a lot of new things in the next weeks. Okay, thank you.
Thank you.
Thank you, Wolfgang. Thank you very much.
You're welcome very much, Marco.
Bye
Thank
bye.
you, Wolfgang.
Thank you.
And good night.
Bye.
Good night.
Bye.
Thank you.